Statistical Mechanics Part 7.
Yes, science! You need to cut out all your loser crybaby crap right now and think of something scientific.
Hello, AJ. Yeah, we gotta study hard. Study till your brain cooks, and then study some more. Hello to you too, Ataro. Trying to understand some Fourier transformation here. I'm located north of Earth. Way north. Or in other words, Norway. The North Way. Maybe the only country that is like named something practical. The North Way, Norway. They were like, oh, over there, the north over there, you know, the Norway, North Way, and the Norway. I always get surprised in the lectures when the professor tells about some Norwegian physicist. But he had some horror stories about one named Onsager, because he was also teaching, lecturing statistical mechanics in some university in England or somewhere. So the students called it statistical mechanics. I haven't watched too much of Magnus, but he seems like a cool guy, of what I watched. It was cool that he was... I saw that he was on Joe Rogan. Admitting that the computer had exceeded his chess skills. All the way up here in north, in the University of Oslo, I'm studying ongoing master thesis in quantum technology and material science, also called condensed matter physics. Yes, it has the physics has consumed my mind. I cannot get rid of it. Thank you, AJ. Good luck to you too. Yes, keep grinding. Goggins would agree. In fact, he's watching me right now. If you get poopy pants, just stare into those eyes, and they'll stare back into your soul. And you will have no choice than to work harder. Yeah, study that chemistry, man. That's like, it's like physics in a bigger scale, you know? And if you think physics, atoms behave strange, well, then you have no chance with chemistry, because that's multiple atoms and particles. So behaving even stranger, maybe. There's some good subjects. It is some of the closest we get to studying the universe. Yeah, math can be pretty satisfying. Just need to keep a good memory so that you remember everything. I should have remembered this 1 year ago. Then I wouldn't need to refresh the Fourier series or transform. But I guess if I refresh it now, I should, in theory, know it even better later on. Math is pure playing. Playing in hell, yes. Hello, man. Welcome to the Quantum Statistical Mechanics. You can feel my pain, yes. My head is cooking. It's like Feynman said, I feel like an ape or a chimpanzee with two sticks, trying to put the two sticks together so that I can reach the banana in the tree. And sometimes I get to knock down the banana that It's equivalent of solving a task. But then the banana is quickly consumed. And it's quickly eaten. So the pleasure of the victory is very small and short. And then it's back to it. Trying to put the sticks back together and strike down a new banana. But I think I got something right here. Yes, because the last atom, the last atom's displacement is equal the first atom's displacement? That's weird. But at least we see that the math is right. Because this is what's confusing me is that here you have an integer like 2 or 4 or 6, but then you divide by big N, and big N is a big number, so that means that it would probably become a fraction, but N is still an integer. That's interesting. So let's imagine I to, let's say 2, so the second atom where N equals 1, and then let's say we have 100 atoms, and then pi. Never thought of making this still be an integer. Because I thought that it had to be an integer for this to be 1. So it doesn't have to be 1, no. This is basically it's an, isn't it like this? 2 pi divided by 100. The pain is getting stronger. Radrag. The longer I use to solve the task, the more pain it becomes. Semper Fi. Then we have I sine 2 pi. Because obviously, when you have some integer and pi, sine will just be 0. Is 0 for 2 pi and 0 for pi. It's like 1 pi, 2 pi, 3 pi. Oops. But what if you divide it by 100? I think we need to check that out. I just can't imagine it. Sign of a because it's not really integer, is it? Okay. Well, this is not good. Means you have to use another analogy. Yeah, you have to use that analogy that... maybe that's why it's a sum. Aditya, you're here to support. Semper Fi, brother. That is encouraging and supporting. Audience also wants to bring the two sticks together so that we can strike down the banana. But if this is... But if the first one is 0, what? Then you have e to the 0, so it's 1 plus e to the I 200 I e to the I 3 pi to the 100. Yes, I can. For this, I'm actually just... what I'm actually doing is I've found the equation of motion of these atoms. These are the same atoms, but the spring constant in between are different. So I found the equation of motion just by adding up the forces of each atom acting on each other. And then for some reason we need, because we want to find the displacement as a function of time, the xn. But then they want us to find the Fourier transform. And I have completely almost forgotten what Fourier transform is, or at least how you find it mathematically. So simply just revisiting Fourier transform. now I'm wondering why k is 2 pi m divided by big N. But let's say we only have 3 particles. And this would be 1. Well, that doesn't make any more sense. But maybe let's just forget this. Maybe it makes sense afterwards. Because I see this is a lot of just math trickery, the Fourier transform. So that's okay to me. I can agree if you just have done crazy mathematical stuff. You don't need actually a reason to do them, but if they end up giving you a correct result, then you can use it. That's okay. But we got... Oh, okay, so it's moving that as well. We got that this and the nth atom k prime n x n time, and then I'm just skipping a bit ahead. You pulled the e inside, and you actually pulled the sum of n inside as well. Okay. So this is okay. But what do you do now? But why are these canceling? When the k's are not equal, if this is equal to 0, then you get just 1. Okay. But if it's not, if it's not equal to 0, then it's just maybe m is 2 and m prime is 1. But there's no sum over that. So how do I choose my case? But it is a sum over k. What the heck? Yes. 2 pi. You're forgetting an I though. Okay, you just say delta k, yeah? Yes. E to the... It's like E... like e to the e to the I. Yes, so what? That doesn't help that it's an infinite geometric series. Are you kidding me?
You need to cut out all your loser crybaby crap right now and think of something scientific.
Okay, Jesse. Jesse! I will do so, Jesse. I promise, I promise. So we have this thing equals, we're supposed to sum over every k, but keep k prime constant. I think there's just one thing I'm missing here. Maybe that's the geometric sum. And e to the I to pi n, yes. N minus n prime. So what? It doesn't help us. And then he says if k is not equal to k prime, it is a finite geometric series. I'll be damned. Finite geometric. I never thought of that. Well, it makes sense that there's some trickery like that. S k prime equals 1 minus e to the I to pi n m minus m prime. What is going on here? 1 minus r. Oh, sorry. And this is to the power n? How can it be to the power n? well, okay, that's so he's just saying x to the power n. Do we understand why it is? So that means it's just no n here, and this is really e I to prime n. Find a geometric series if k is not equal to k prime. That is, if m is not equal to m. And how do you see that? You just throwing it in my face, not explaining? Or he is explaining? Or no? Let us see. 1 minus. And how is 1 minus Rn equal to 1 minus 1? What? There's some explaining that needs to be done here. Because this is equal to 1. That is not true. M prime can be whatever it wants. M can be... or M prime must be one number, I think. And... but M can be... R, but he says R is not 1. Yes, it's an integer. But isn't this a bit contradictory or something? That he says R is not equal to 1? And then he puts... Okay, so R to the n is 1. But R to the n. Oh yeah. Yeah, I forgot. Yeah, when you don't. Yes, you are. Yes, exactly. Exactly, Manan. Yes. Because that was what was bugging me on last page. Because, you know, normal R. I was like trying to think about periodicity, and I think I've been explained some other kind of way this Fourier transform. But when you divide by n, it's like, well, it's not an integer. Because 2 divided by like 100 atoms, that's not an integer. But here, yes, he's removing the n, or divided by n. So then, anyways, whatever m is, this is constant. Yes, exactly. It's very funny that I actually can get help from guys on the live stream. That's really fun. Because normally I'm just used to sitting alone and going into these dark holes of wondering why and why and why. And someone actually from the live stream can give a hand. That's amazing. So the n, that is 0, 1, 2, n minus 1 up to. Yes, so that is an integer. But still, I would like an explanation of how you can see that it becomes like this. Because this this came out of a black hole. This sum, I agree. Totally agree. But I guess it's like a geometric series that I don't know of. So that shouldn't be too hard to get. But okay. This suddenly becomes a geometric series like this, and it's 0 when the k's are not equal. So, because if the k's are equal, this is a sum. There's also a sum over k, so doesn't that mean that some k would be equal to k prime in that sum? Yeah, so that's the term that is not 0. You could just factor it out, I guess. But is it then allowed to call it a geometric sum? Or a geometric series? If you just throw out one term? It starts from a squared. Yeah, it starts from ar squared. Okay. Let's see. Constant, then the r thing. It's plus. Yes, you multiply. Okay. But what I'm wondering, let's say that isn't one of these terms, aren't they, because m prime is like, could be like 2, I think. So that would mean that in the middle of the geometric series you would get to m equals m prime, and that would be when k is k prime, so we actually get like a surviving term. But how can you then pull out the term where m is equal to m prime? Because shouldn't it be, is it allowed to say that this whole thing is equal to this if you pull out one of the terms? Or are we pulling out one of the terms? Yes, it's equal to 1. The rest must be minus 1. Holy. Yeah, the whole series sums to 0. Yeah. So does that mean that if we can this be clear? We're just focusing on this. Does that mean that it is maybe it should be allowed, I think. No, maybe you can't say it. No, you can't say the summation sign then. But this whole thing would then be equal to the first, or okay, let's imagine for simplicity that m prime is 0. So that means that the first term is very clear. The first term would just be 1. And then it would be plus the next terms. And that means that all the next terms combined is equal to minus 1. Yes. Yeah, because it's just n. Oh, maybe I was too quick, maybe. Because I already started summing up over the case. Because here everything will be summed over k. But this sum, that's what this is talking about. That's just for one k. Maybe it's don't need to write. So. Because we're saying that this is the geometric series, right? Yeah, I should write out a few terms. That means that this is a geometric series for every of these k's. So the geometric series is supposed to have, yeah, this is the n that makes it a geometric series. Now it makes more, that part makes more sense now. Because I was thinking, how is this a geometric series with the k's? And then I saw you writing AR to the 0, AR to the 1. I was like, I was like, where are the k's changing in this? But they're not supposed to change. Because k and k prime are both fixed numbers in this geometric series. Say that k is 1 and k prime is 0. Let's jump a little bit ahead. Let's say, because we know if we start at this, and let's say that k prime is equal to 0. So then we obviously we have to start at k equals 0, 2. In this sum, so we would get and then we have 0 here, so a sum over e to the 0, e to the sum over 1 is just 1, it's 1. And then when we test, now we test k equals to 1, then we get a whole nother term in this k sum. Oh, sorry, didn't see. Now test k equals to 1, and k prime must always be 0 because I don't know, we just set it to be like that. Mathematical trickery, I guess. We just multiplied with e to the minus I k prime. And there's no sum of k prime, so. And then this would be always 1 minus. It would always be 1 minus 0, that's just 1. So with every term would be I n, and then you get like, you start from 0, and then you get like this sum will give you a term in this sum, whole sum. That should be really e to the first n 0, that's also 1. Am I missing a pi somewhere? I need to think of mistake of thinking of it was actually good to just write in terms of m's. So m is 1. That means that k is not 1, but k is 2 pi. 2 pi m is 1 pi over, it's 2 pi over n. So the next term would be e 2 pi times 1 over n. Next term e and I, of course, 2 pi. No, sorry. Then n is 3. No, n is 2. This is just 1 pi. This is 2 pi. Yeah, so then you can maybe plus all these terms up to e to the n minus 1. Yeah, is it just, yeah, because n, oh shit, it is 2 pi. So this is 4, right? N is 1, n is 2. So when k is equal to 2 pi, okay, then k times n, and when n is n minus 1, 2 pi, okay, so it's like 2 pi n over n minus 2 pi. Check that again. Flying tongue is this? 2 pi minus 2 pi over n? Ooh. Well, this is really 1, right? Just cancel that. So the last term is e to the minus 2 pi I over n. You gotta be kidding me. So maybe it doesn't matter, they just... You said that the geometric series was... geometric series. The camera, when it turns off, it makes this sound. It's like, did it? It scares the shit out of me. The whole sum is just equal to S. To S.
Liar.
I'm just kidding. It was my wire moment. You're back. I've written out what the geometric series would be. 1 and then this and then this. I was completely forgetting that k is constant inside there, and it's just n that makes it, as you said, the geometric series. And then I figured out that the last term of n equals n minus 1. The last term is just minus 2 pi I over n. But okay, that's okay, but now I will just try to I'll figure out the geometric sum as I've written out the terms, and you said it was A times oh shit, that was amazing. This was A. That's R. And this was R to the power n. Yeah, and I really just said that m prime was 0. Yeah, so I just said that m prime was 0. That would mean we get no A. A is just 1. A is just 1. Yes, so you have A, and then you have the next term is the same times 1. The next term is the same times 2. Yes, then we have a geometric series, but the last one is a bit weird, maybe? Does the geometric series have n minus 1? last term must be, you just take 2 pi I over n, then it times n minus 1. Yeah, it is 2 pi I, that's just e to the 2 pi I is 1. And then you get 1 minus 2 pi I over n. It's a bit weird to have that as the last term, but maybe we don't give a damn about that. Maybe if the term is weird, well, how nice. It was this. Yeah, it's not. But it doesn't matter, right? Geometric series can have go up to n minus 1, I hope. So I basically, at least just yes, yeah. I was just like nitpicky. Just wanted to see what the last term was, but I guess it doesn't matter because it still follows this, still follows the geometric series. The sum of a geometric series is there's a to the small n, not big. Isn't it big N? Yeah. To me, the proof on this matter, I rest my head against a mathematician that he has find the proof of this sum. At least when my goal is to prove the Fourier transform. So here they really assume Yeah, so then r the n minus 1 over r minus 1 would be e to the e to the 2 pi I over n minus m divided with n minus 1 r minus 1 this that I'm doing the reverse algebra here. That must be 0 because this is 1 and that means I have to change page. I hate changing pages. I wish I would have like just a continuous page. It should be like the notebook should be like a roller, like just like an iPad. You could just roll, and then it would have to be some crazy mechanism to manage it. But if I just drag here, I could drag the previous page back. Finally a new page, yes. A clean start. But I need something from here. We had that big thing. I am from a country way north. So north that they call it Norway. A proud representative of Oslo University. Semper Fi, that is correct. But it still isn't that big. The number of people in Norway is just a fraction of the number of people in big cities around the world. That's crazy. And thank you, by the way, for the big help. Yes, that's crazy. With the mana of Manan, we finally came one step closer for enclosure. So we have this thing now. This is N. Every term is 0, yes. So oh yeah, okay. Oops. Back to the filthy page. I said here this, but if when m prime is 0, m prime is 0 and k is 0, this is just 1. So for the n0 is 1 and yeah, so then you get the 0th nth 0 term, n equals 0 term is 1, and so you count the 0th term, yeah, so then you get n to minus 1. That means you just remain of n. So yes, then we also understood where the n comes from, because I was really wondering about that. I thought this was just some normalization, but actually it just arises. So it's n times ck prime. Whew. Rolling forward like a old Panzer tank, slowly crumbling over the dirt. Yeah, so you can say it like this, but I don't need to look at anything that I don't need to look at. Insert it, yes, nk prime. I agree. That represents exactly the right hand side of your image, yes. Nope. I have to go back. To this big thing. So with all this mathematical trickery, we started here, multiplied by the sum e to the prime. So here we are, and then we say that ck is this. How can you say that it's ck and not ck prime? Sum n minus 1. Sum n minus 1. So just relabeling k prime as k. But is that allowed? Yes. Because the left hand side only has no k dependence, and we multiply by minus k prime, but we threw it all. No, wait a minute. Yes, because no. The left hand side has k prime. And then we look at the right side, has k prime and k. But then we found out that the right hand side just has k prime. So if the right side has k prime and the left side has k prime, then we might as well call it k. Alright. Writing it down so that I won't, so if I forget it I can maybe re-understand it if I look at these notes. Shit, it's minus. It's okay, that's okay. Because it was minus k prime. Many authors move the factor 1 over n. 1 over n half to the forward transform. And half to the inverse. so that both look similar. What? And XN. G was initially. Like this. Would that mean that this is true? Or this is this some loud stuff? It's on not the loud stuff. Is this what we have to do? Put it in the list. What the fuck? What? This can't be true. found that ck. Plugging that bit to the trial expansion produces xn of t. Xn of t is ck. Everything is correct but slightly lopsided. What? Slightly lopsided? I'm just using it. I'm just using it to try to explain the Fourier, the proof basically, or derivation of Fourier transform. It is surprisingly good at I think I have the proof in my notes, but those notes are 1 year old and they're pretty ugly. So I don't think I dare to rewatch those notes of the Fourier transform proof. But I'm just... Yes, exactly. All fine, and this is the problem I'm working on, actually. I found the equation of motion, and then to find xn and yn, I had to do a Fourier transform. Then I use the oracle as my sparring partner. Sometimes it's like, of course, you need to try first yourself before you look at the solution or try to find help or some guide on the internet. But sometimes I'm like, I've been trying for some time, and then I think, okay, now I need to get some help. This is taking too much time. And when I'm like formulating a question, because how I use Oracle is I pretend that Oracle is a teacher, like a group teacher in group sessions when we're working on problem sets, and I pretend that I'm there in class asking, well, how do you get like this, and this? And when I'm formulating the question to Oracle, I very often, I just, aha, okay, that's how it is. So when I'm not like pretending to be in a group session discussing with the teacher, I tend to leave some brain power out. But when I'm trying to formulate the question, like I'm doing here to the Oracle, many times I'm like just figuring out the answer while I'm formulating my question. Try a solution of the form e to the I f of x. Yeah. I think that's what the Fourier transform is doing, right? But it's slightly lopsided. The forward transform carries all the weight, 1 over n, while the inverse, why is it so important with the inverse? I just want the forward one. I don't care about no inverse. I'm not going backwards. The inverse carries none. Most physicists prefer a symmetric or unitary normalization, in which each direction of the transform contributes the same factor. Well, you know a lot of the building blocks for it. So it's gonna be easy for you, brother. You're just in, I don't know, college or high school or something? Like 12th or 11th, 12th or 13th year of school?
People need dramatic examples to come out of apathy, and I can't.
Then you have a bright future in front of you, brother.
From flesh and blood, I can be ignored, I can be destroyed, but as a symbol.
You probably have talents in math. But if you combine talent
What symbol?
with grinding and working hard like 𝐿𝐿𝐼𝐻𝐿𝐼𝐻,
Elementals.
then you can achieve greatness. Because you know science is cool. If you just get past through the hard learning, and when you can apply your hard learning, then it's pretty awesome. But you first need to know the stuff, and that's really hard. But when you know it, it's a goddamn roller coaster. And it's just going upwards fun.
Yes, science!
Yeah. Jesse says it best. This is really weird. You would say that the one thing is 1 over square root of n, and the other is 1 square root of 1 n. Most is a unitary normalization, okay, in which each direction of the transform contributes the same factor, 1 over square root of n. That is the only thing that happens between 𝐶𝐾 t and the tilde coefficient. Please show me how you plug this in. You're gonna plug this beast inside here? Well, good luck. I'd like to see that. Introduce a new name for the coefficients that absorbs a factor square root of n. Okay. X tilde is equal square root of n times ck. ck. Okay, we have ck here. ck has xn in it. This is just some normalization stuff. X tilde K T. Okay, okay. So are you saying to me that I should plug in, say that CK is equal to CK? This is the CK we found, yes. Multiplying both sides by square root of n. Well, this was a little bullshit explanation. What you really should do, and the Oracle, you should learn about this. That's, you should say, if you really want to go step by step, and turn over every stone, so that you never misunderstands. CK T. We have this one expression of it. Obviously CK of T equals CK of T. It's maybe too obvious to write, but at least this is necessary. N X tilde K T equals 1 over n. Sum n minus 1 n. X n t e to the minus I k n. That means that x tilde. So x tilde is not the inverse, right? Or. But now we haven't really solved for xn. And why are we just... Okay, so this... But it's really a normalized CK. It's not a normalized XN. This is basically... Yeah, this is CK times square root of n. Now we're just saying CK. So we're not going back to this. Not going back here. But I'm not interested in C tilde. No thanks. Rewrite the inverse transform. The one that reconstructs Cn from the coefficients. Insert Ck equals tilde divided by n. And we did this. Yeah, okay, so that's what we did here. Now he wants this. He wants to put this. Put this in this. Okay. Yes, that we got that. Which is exactly the line you see in the screenshot. I'll be damned, Oracle. I'll be damned. How the heck was this a Fourier transform? Fourier transform is basically nothing. Fourier transform is just like summing over some coefficients. I guess you could say it's integral, but we're having it discrete. Okay. So that's a note we need to write. And B. So, yeah, so it's really right to say. So it is the same as saying this. So it is correct to write it like this. But I like it another way. Welcome, Harmony Hype. Sorry for a late reply. So you're not getting dizzy from watching these mathematical figures. That's a good sign. Right now I just worked out the Fourier transform of y when you have this equation of motion. You can guess the solution with the sum of k's of ck times e to the I k n. So I think it's really that you guess the solution and then use Fourier transform, because the atoms we are working on, it's a material that is one-dimensional and they are same atoms, but the forces between them are alternating differently. You could say that there's two different springs between them. So I wondered, I didn't remember the Fourier transform, so I had to look into how it's done. I think I figured it out. Are you also studying physics, brother? No worry. You should just ask a few why, then nobody really understands any of it anyways. resource. This is Mrs. S. She's like a group teacher in our course. Now we need to understand these notes. And this here I was asking Oracle ChatGPT about the Fourier series. It's much more faster than to like Google and find some document that tries to explain why. And then they are always explaining in some weird way. And then I can't ask why they did it because I can't talk to the professor that made the notes. But here, I can ask any question I want. And it does a damn good job of explaining it. Surprisingly. This is the new Google. I think I learned about Fourier transform some years ago in other courses, but I didn't actually understand it that good. But now, after a discussion with Oracle, I think I do. I needed to find xn and yn, the displacement of the atoms. You see? Because there's different forces from these springs if you imagine these atoms being displaced in different positions. Like this xn could be right here, or this xn could be here, and then this spring will pull on it that way, and this spring will also pull that way. And since this is like repeating scheme, every atom experiences the same. You could use Fourier transform because Fourier transform is like a repeating thing. This is really a static back and neck exercising. you see that xn depends on n, but not k. Or yes, it does. Son of a... Maybe not. I think the thing is that xk does not depend on n, because inside C of k does only depend on k, because you sum over all the n's inside C of k. So n dependence disappears. But inside x of n, you get only n dependence because you sum over all the k's. So that is useful because so now we really got this. But what is weird is that is this thing summing and summing without k? That can't be. Because you started with x. You started by assuming that xn was ck. I can then. This is obviously inside the sum. Right. So when it's summed over, it really started like we started like this. Yes. Well, there's the k summed over there. So if I fill in ck, yeah, this is not parenthesis there. That's wrong. It's really that this is in parenthesis and this alone. In the parentheses. Then it's correct. Let's take a square. So we have figured out that xn T equals this. Oof, you really have to keep your tongue straight in the mouth, or how you say it in English. xn 1 over this. Yes, sir. You're goddamn right.
Liar.
Oh, I meant this.
Yes, science!
That's what I meant. Oops. Oh, sorry. Now you can see it. Yeah. So then we have shown this. Yeah, that's good.
Yes, science!
You're goddamn right, Jesse. So the next is to insert this. You really have to keep your mind straight with all these sums, because when you really carefully look at the sums, it makes a lot of sense. But if you don't, you get in a hell of a mess. We have a lattice index and n integers limit nth mass of the mass in an infinite or more often periodic chain. Yes, the displacement of other mass. Xn is a function of a discrete variable, the continuous variable t. Our goal is to rewrite the dependence of n in terms of waves. Yeah, k is really the wave number. It's a mode. This is our y waves, physical motivation, because it's coupled spring equations of motion. Yeah. All the atoms have these equation of motion. They're linear in the displacement. Okay. So solutions of linear translationally invariant systems are sum of plane waves. Need to dig a little bit deeper in that. But first, we need a food break.
Liar.
back.
got it.
signals and systems? Galva, you're back! It's going okay. Slowly forward.
Liar.
𝐒𝐮𝐲, this is some delving into some Fourier series, and it was here because of some condensed matter physics or quantum statistical mechanics, or you can say quantum statistical mechanics. Or wait a minute. Yeah. It's because it's a harmonic solid. And I'm supposed to calculate the vibration spectrum of the lattice. So then I've found the equations of motion. And then to find xn, you could Fourier transform 𝐿𝐴. Yeah? Right now I think it's weird that a Fourier series is a sum of plane waves, and I don't understand how in the name of Mother Nature a sum of plane waves can equal a displacement of an atom. See, this is x1, so x1 is like 1 centimeter or something. It means that sum of plane waves would equal 1 centimeter. That's really weird. I think the brain is deep fried. I think this stuff is really simple, but my brain utilizing quantum mechanics cannot compute it. I think I need to forget this a little bit moment and look at why it's I. Yeah, that's cool. I think I used to have one, but I don't see how it work. How I can use it here, because it wasn't Fourier transform. I remember if you have yeah, if you like play a frequency, a sound, then you could understand what you could find out what that frequency was if you some way use the Fourier transform, because it like goes through every frequency and checks where the integral or for so if you hit it was something like sine squared or cosine squared. So when you had the integral of the and you were testing over the right frequency, you would get an enormous contribution in integral. It allows you to draw Homer Simpson? God damn! Now we're talking. I wonder why the plane waves are exactly 𝐼𝐾N minus omega t. I didn't get no link. Maybe you need to try the whisper again. Oh shit, you add them up. Holy shit, there's some real linear algebra here. Ooh, Twitch, yeah. That why you're Bart? Or Homer? Whoa.
In a previous video, we learned how a complex Fourier series can be used to describe a solar system consisting of a single planet and a moon with a complicated set of higher-order moons. Although such a system turns out to be somewhat unphysical, we saw that by carefully adjusting the orbital radius and initial phase of each of the orbiting objects, the final moon can be made to trace out any trajectory we can imagine. This result is pretty remarkable, and if you're not familiar with Fourier series, it might seem almost magical. In fact, the previous video was focused entirely on explaining the details of how this magic comes about. Now, as many of you are probably aware, Fourier series has been around for 200 years, and a quick Google search will yield many examples of interesting orbits. Perhaps the most famous is one that's in the shape of Homer Simpson, as first demonstrated by Santiago Ginobili back in 2008. Whoa. In all honesty, it's pretty hard to top Homer Simpson. Therefore, rather than simply showing yet another interesting orbit, in this video, I'll focus my attention on the intricate details to give you a closer look at how all the spinning arrows work together to create the final image.
Personally, I find the visual display you're about to see to be truly spectacular. Spectacular almost beyond belief, and I really hope that others will find it as extraordinary as I do.
As a quick reminder, recall that any two-dimensional trajectory can be written as a complex Fourier series, where each term is a time-dependent complex number that can be thought of as an arrow that rotates at a specific frequency. To calculate the sum, these arrows are added vectorially, which means the tail of each arrow is placed at the tip of the preceding arrow. In this particular case, we'll be adding a total of 251 separate arrows together.
We begin at a magnification in which the entire trajectory will ultimately be visible. At this scale, we get a good view of the largest and slowest arrows. Of course, the details of exactly how the trajectory is being drawn can't be seen. So let's zoom in a little to get a closer look. Now we can make out a clump of tiny arrows buzzing around like a swarm of bees. Interestingly, when the conditions are just right, the arrows conspire to fling the trajectory around like the end of a whip. It's really quite beautiful. Unfortunately, we still can't make out what's happening with the smallest arrows. So let's zoom in a little more. And while we're at it, we'll slow things down a little as well.
At this scale, we can begin to see the swarm as a large conglomeration of tiny spinning arrows. Notice how large groups of arrows seem to oscillate together to push the trajectory around in different directions. To me, this level of magnification really starts to reveal the intricate and complex nature of how all these arrows work together to produce the final trajectory.
If we freeze the motion and simply look at all the individual arrows, you can really get a sense of how involved this process is. I mean, just look at all these tiny arrows. It's absolutely amazing. And if we zoom in just a little more, we can finally make out the details of the smallest arrows.
At this point, we've zoomed in by a factor of 1,000. The final arrow seen here is approximately 5,000 times smaller than the largest arrow we saw at the beginning. Although things can be a bit dizzying at this magnification, we can now see pretty clearly how each and every arrow is simply rotating around the tip of another arrow, with the tip of the final arrow drawing out the resulting image. Remembering that there are 251 spinning vectors that go into making this trajectory, it's hard not to marvel at just how incredible this process is. As we begin zooming out, we start to get a sense of the large number of arrows at play and the vastly different sizes of these arrows. It's here that I can start to appreciate the elaborate and somewhat convoluted process that's actually taking place. As we zoom further and further out, we lose sight of the smaller arrows, but the swarm reminds us of the incredibly detailed and complex motions taking place. And of course, it's worth keeping in mind that the key to this entire process is the calculation of the Fourier coefficients. It's these coefficients that provide the length and initial orientation of all the arrows, and which ultimately leads to the final trajectory shown.
Whoa. But so in my case, in 1D, I have like this amount of arrows, and they're like multiplying, and no, they're like adding and subtracting each other until I get the displacement I want in one direction. Or you could, maybe you can just take it out in the complex plane, then you would get 2 dimensions. It would sort of be like if we would like change the variables to what's it called? Polar coordinates? No. Spherical coordinates? Yeah. Mr. Gall. We can. This is the one. And then I'm on, I think yes, I'm on number 2. And you could write this is basically our system, equal atoms just alternating spring constants. So there you will basically just get a force on the atoms if there are any displacements. So then you can get these equation of motions, just depending on the nearest neighbors. So this one is affected by this one, and then we say that that's our subsystem, because that subsystem is really repeated until you have gone through your whole lattice. So when you're written up the equation of motion, we are trying to find the Fourier transform. So I've come. I understand this. That you can get this because of the translational invariance. But I'm missing. I'm missing the omega t part. need to really understand next time. I'll be back in some hours. Gonna have a training session first. And then we really need to understand and King. It might be that I understand it now, but maybe I've been working too much of it so that I've brain fog. But we have to make sure next session. And I think I now understand the math behind it, at least. That was difficult too. It was like sums and geometric series and etc. So I really lost track of what the physical meaning of it was. I just focus on the symbols and the math. So next session we should really focus on what these symbols means. One thing I really know or feel more confident in is why it's E. It's EI because it's repeating, you know? The arrows are repeating. But I need to understand why exactly these terms and why there's minus, for instance, omega k, the frequency, and why it's just times t, why is it not t squared, and the k is exactly like that. I think the k is something about when you sum these arrows up, they all become something. So I'll be back, and thank you, ladies and gentlemen, for watching and helping. Yeah. Yes, maybe a simpler one, yeah. That's always a really nice and good idea. And it's always so clear when for the more advanced one. Yeah, that's true. Because it's a little bit confusing if we're using K, and then it's K spring constant. But maybe, I hope they're not the same. No, they can't be the same. They're just completely different, yeah. Luckily, the K's are the modes. Yeah, that's a good one. Well, I'll be back. See ya.